between head bustings, he's taking a little cardio break. But he doesn't want to spend too much energy. He just wants to go light because he's going to have to bust some heads more. So he's going to jump in one of these angles. We don't know which one. And the forces that are acting on him are just gravity. And this is the full body diagram. And X and Y direction, we have the 12 meters in the X direction, and the change in Y is 3.75 meters. So this is a little backwards than other problems where we know the change in Y and the change in X. We don't know the velocity, the beginning velocity. So, or the angle, we're going to take the tan theta, and we're going to take the velocities of the y and the x, and we're going to take tan theta of that, and that's going to be our angle. So for the beginning of y velocity, because he's got to go up this way, we're using this formula, and the final velocity is going to be 0. We're going to call that 0 because I'm sure he's not going to do anything when he gets to the bottom. So then anyway, algebraically, this is what we get. And we plug it into the quadratic equation, which is this, and we put in the change in y over here. Now this is the change in y, but then we got to figure out this change in y, because it takes more time to go from here to here. So we're going to figure out how to get to this point here. What energy, what's the velocity he has to jump to get there. And plug in some numbers here, and he came up with, he wants to jump 9.625. And that's that belt booster territory. So he is going to be jumping 13.73 miles in the air, and this is going to take him 3.4 seconds, a leisurely pace. So what it turns out is that the less he goes the more he goes this way, the faster he goes this way, the less he'll have to run this way. And that's what he's after. He's after a nice leisurely stroll. So it takes him 3.4 seconds to get to this one. But to get to this point, it takes him twice that. And then, after that, he's got to go down another 3.7 meters, and that's going to take him 1.8 meters, which equals 8.6 seconds. So all this to get to 12 meters, change in x over change in t equals 1.8 meters per second. That's how fast he's got to run. Pretty doggone good. And you take that over 13.73 get you 84. I'm sorry. This is 1.4 seconds. Even better. We get 84 degrees. That's the angle. Because we take the tan of that. Oh, anyway, on his way down, he sees a goon. He's got to smash his face. So he's got to calculate what the speed is going to be on the speed of his boot onto this guy's face. And this guy is roughly 2 meters tall, and we're going to take the final velocity equals initial velocity squared, final velocity squared, initial velocity squared plus 1/2 a change y. Anyway, we get, because the initial velocity is 6.87 meters. We figured that out. That's coming from here. Velocity is 0 to here, 6.87 meters per second, and then we figure out that with the new change in y, because the goon takes up 2 meters, and we get 7.5 meters per second. That's like 16 miles an hour. That's a good boot to the face.